We move to the next speaker, is Veronica.
Hi.
Hi.
I'm sharing my screen.
So it's on QCD. Actually, I realized that all the talks have QCD in the title, except the last one. But then the third to last one has QCD in the title twice. So it was a preservation of QCD in the title. And so this is all about QCD phase diagram with charge and isospin axis. Go ahead, Veronica.
Thank you. Can you see my laser pointer?
Yes, yeah.
And okay. So this talk is a little bit different, coming from an astrophysicist, but I'm still interested in QCD phase diagrams. And as I already seen this morning, at least for me this morning, in the previous talks, all modern approach, or many of the modern approaches to QCD are also worrying about what happens when the temperature is low enough to reach the domain of neutron stars. We're seeing both talks showing also not only comparisons to lattice QCD, but also comparisons with neutron star masses and radii. In the old days, we used to refer to neutron stars as having leptons as the main difference, but now we know that the differences are much more complex than that. And my talk is going to focus on how do we compare the results that are obtained from different approaches, like for example, when you compare results that are coming from heavy ion collisions with results coming from different astrophysical scenarios. So we have many examples of different QCD phase diagrams, but what many of them have in common is that they're usually shown in 2D. And the ones that have a finite baryon chemical potential usually are shown as a function of also temperature. But I think something that's important, especially when we do these comparisons that I was talking about, is to look for how these are affected by having a different amount of hadronic or quark charge or isospin. Also, I'm going to discuss a little bit how these quantities relate, because traditionally in the heavy ion community, people always discuss quantities that are related to isospin, and the astrophysical community, quantities related to charge. That's because historically, the hadronic charge will balance the lepton charge, and lepton fraction is the quantity that would go into all the supernova simulations. But anyways, the relation between these quantities is not trivial if you have a net strangeness in your system, which is the case when you're making comparison with astrophysics. And I also going to discuss a little bit about the effect of strangeness, net strangeness in phase diagrams. So the model that I'm going to use to create these phase diagrams that I'm going to discuss is the Chiral Mean Field model. This version is a little bit different than the one that Jan has already explained in the previous talk. It also contains baryons and quarks, but here I'm not including particles that have negative parity. And the way the degrees of freedom change here is not using excluded volume, but instead using this field phi, called phi in analogy of the Polyakov loop, which is the present in the calculation of the effective masses of the particles. And in this way, the particles might become more massive or less massive, depending on temperature and chemical potential. And in this way, you can change degrees of freedom in a very steep way, reproducing a first order phase transition, but also in a very smooth way, reproducing crossovers. Because usually in astrophysics, what we have for modeling is having a model that has hadrons, a model that has quarks, and it just merges them together where the pressure becomes larger. And what happens is this all can only give you a first order phase transition. I also have a potential for this field phi. It was built in analogy to the Polyakov potential from the obtained from PNGL reference. But as yesterday, Alexei Vanitsky has already discussed in detail, there is a reason, and there are advantages of having also density or chemical potential dependency explicitly in this potential. And this is also going to allow me to have a phase diagram that more or less fulfills the expectations of the community. So this model is fitted to reproduce nuclear physics, and by that I'm talking about saturation properties. Astrophysics, we have tested in many different ways in astrophysics, calculating stellar masses, radii, cooling, and other quantities. And also I'm going to show you later in neutron-star merger simulations. This model was built constraining some quantities to lattice QCD. And also we checked recently and found that it's in agreement with perturbative QCD in the regime relevant for astrophysics. So now I start discussing my results. So first of all, I'm going to constrain my net strangeness to 0. So I still have strange quarks and hyperons, but only if they match the amount of anti-strange particles. So no net strangeness. And I'm going to show phase diagrams as a function of temperature, charge fraction, which here is just the amount of charged barons or quarks divided by the total number of barons and quarks, and the Gibbs free energy. So the Gibbs free energy, the quantity that will be the same in both sides of the deconfinement phase transition when you have an external quantity like charge fraction as being fixed. The chemical potential will not be. So this is the quantity that will be taken if you take a derivative of your potential with respect to the number of barons. And before I show the phase diagram, I just want to say that the way I like to think about zero charge fraction, and I explain this because many people used to think just about isospin. So at equal to 0, when the strangeness, the net strangeness is set to 0, this will just be going from pure neutron matter to matter that has twice the amount of down and up quarks. And then charge fraction 0.5 will be going to matter that has the same amount of protons and neutrons to the one that has the same amount of up and down. So keep that in mind. And when you draw this, and I just want to emphasize that this has influence from the quark side, but also has a lot of influence from the hadronic side. And what we found is, and for me, it's easier to just look at it equal to 0, the bottom slice here. You can see that this phase diagram changes with charge fraction, that as you go to larger charge fraction in the back of the figure, you see that the phase transitions to push to a larger free energy. And this has to do with how this more symmetric matter affect hadronic and quark phase separately. So in the quark phase, you're switching from having 2 times the amount of down to have the same amount of up and down. The hadronic phase, this is much more drastic because you're switching from having just neutrons to the same amount of neutrons and protons. And this change will be much larger for the hadronic phase. And as a consequence, the hadronic phase will soften much more than the quark phase when this more symmetric case. But you have to be careful when you're talking about softening. As an astrophysicist, I always talk about P versus energy density. But when you translate this to P versus mu, which is what you did to draw this phase diagrams, these things don't always relate one-to-one. Sometimes larger pressure in one means lower pressure in the other. And that's what happened exactly here. A lower pressure in the hadronic phase in P versus epsilon will mean a lower one in P versus mu here. And that's why the phase transitions push to higher free energies at large YQ. But what I care about as an astrophysicist is that I like to think the other way, is that the lower YQ will push the phase transition to lower free energy. And that's great because it means that you have a more asymmetric system, as it is in neutron stars, for example. You have a lower threshold for the deconfinement and better chances of finding quark matter in your stars. And this has to do, I cannot emphasize enough, has everything to do with the particle population that you have on either side. So the reason I'm using this effective model is just a way to create these particle populations, which I further analyze how they change with the charge fraction. But I know that many people don't like to look at the free energy because they are used to look at the baron chemical potential. The only downside of this is that in this case, you have to look at 2 different phase diagrams, on the hadronic side on the left and on the quark side on the right. The quark side is pretty much the same as the bottom figure, because I put a formula here again that differentiate by this term, that depends on the charge chemical potential. The charge chemical potential is very small in the quark phase, because again, this charge chemical potential has to do the difference between protons and neutrons or up and down quarks. And this difference is much smaller in the quark phase. So these are almost the same, the red and brown plots. But the green and brown plots are substantially different in all the region that's not the largest charge fraction, where mu cube is 0, or smallest charge fraction where YQ is 0. So otherwise you have a different phase diagram. It's a little bit hard to see things in 3D, at least for me. So I like to always plot things in 2D too. And that's what we did here. So first I'm showing the bottom of all those phase diagrams, the one for the free energy and 2 for the baryon chemical potential. Those are the colorful curves here. I'm keeping the same colors. But now I'm adding curves in black, and these are respective curves, but now for strange matter. So now you allow for net strangeness in the hadronic and quark phases. And as a consequence, you have much more strange quarks and much more hadrons. And the difference is not very large. I'm talking about substantial difference between the colorful and black curves. And I want to focus on the free energy again, because otherwise you also have to talk about the charge chemical potential. So if you just look at the black and brown full lines here on the bottom left, and the difference only appears in the bottom left because if you have large charge fraction, the hadrons will be suppressed. And if you have smaller charge fraction, the hadrons will appear before the confinement. So allowing or not for a low temperature for net strangeness to be there will again change the position of your curve, because it's changing this relative stiffness between the phases. So you're adding these hadrons, the hadronic phase is getting softer. In this model of the current parameterization, the quark phase at equal to 0 doesn't get strange quarks right away. The strange quarks appear later because they're more massive. So everything is dominated here by the appearance of hadrons that soften the hadronic equation of state and push the phase transition to a little bit larger free energies. And now I'm showing you the top side of those phase diagrams. Again, the colorful ones correspond to known strange ones I already showed, but now I'm adding these black lines for the strange matter. And here, at the very top of my phase diagram, at least the part of the phase diagram I'm showing you, and you can already realize that I'm not talking about critical points on purpose, because I'm only concerned with the position of these lines at the moment. So what I find is that we're changing, everything is pushed to much larger free energies of baryon chemical potentials. And the effect here is different, because at large temperature, now the effect is dominated by the large amount of strange quarks that appear. And they are turning matter more soft on the quark side. But so far, I've been discussing only the charge fraction. So I copied the same figures from the previous slide on the top, and then 2 figures here on the bottom that have yi in the x-axis. So I want you to pay attention a little bit to this relation that I put on the top. I think when we say charge fraction, what most people think is just a 0.5 shift from charge fraction. And that's because most people are used to think about the condition of having 0 net strangeness, which is the condition, for example, in heavy ion collisions. But if you're talking about making comparison with astrophysics, we have net strangeness because we're talking about events that happen between milliseconds and millions of years. So there's plenty of time for strangeness to be formed. And what happens is this affects this relation. And this shift is not a simple shift, because the shift that depends on everything else. So the shift will be different in every point of your phase diagram. So now looking at the bottom left figure, we see that the only shift is, again, because it's shift in principle is 0.5, but we have to, where strangeness is present, it won't be. You get a large difference from just having a horizontal shift of 0.5 in the hadronic component, which was the one that had the amount of strangeness present. But at large temperature, there's a huge shift, and this huge shift affects all your curves. So if you're looking at the top of this phase diagram, all these black curves would shift to a much larger isospin fraction, and in some parts will be positive, which is a little bit weird. And the reason this happened because right now I'm making these curves with charge fraction between 0 and 0.5. So these will correspond to an isospin fraction, which is even a little bit positive. But of course, I could have calculated this fixing the isospin instead. And by the way, we have written a different code where everything works as a function of isospin and verify the results, in addition to using the simple formulas. So summarizing a little bit of what I talked about so far, heavy ion collisions have a very large charge fraction of, if you're just counting, for example, gold, and lead, this would be about 0.4. But the thing is, if your collision is too energetic, then the nuclei just pass by each other, and what will be formed behind is isospin symmetric. So above 0.5, I would say, above 0.4, I would say. In cold catalyzed neutron stars, if you had just neutrons, you have a charge fraction of 0, but you can also form pairs of protons and electrons, increasing the center of neutron stars or charge fraction to about 0.15. Of course, this is a bit model dependent. In supernovae, people have been studying this for a long time, and there is very complicated because this is a very explosive phenomenon. So depending on the exact time that you're talking about or the exact position, this varies a lot. But I decided to write numbers here that are all over the place, but the canonical value that people like to go back to when they talk about supernova is 0.4, meaning it still has more of the original protons that are going to become neutrons later on in the explosion. But an interesting question is, where do neutron star merges fit in this picture? Are they more like supernovae? Because they're hot, they have a large entropy per baryon, so many people like to compare them to supernovae just being a little bit hotter. But what I found out is actually quite different from that. So we did some calculations for using this version that I explained already about using the Chiral Mean Field model in a hydrodynamic, general relativity hydrodynamic simulation. And this was performed by the group of Luciano Riazola in Frankfurt, and more specifically as Elias Most. And before showing these results, I'm going to spend a few minutes discussing this background. So I just showed the 2D version of the Chiral Mean Field model. And to do that, I had to choose a random charge fraction. Here, I just chose a small one, just to show you that you go from having just quarks, just hadrons on the left to quarks on the right at low temperature. And as you go up, you end up finding this crossover region, which in our model happens at 160 MeV temperature. And what I found out when you plot the simulations here is that they cover sort of the whole phase diagram. So we have to find ways to show this. And the way I'm showing you today is just tracking the most hot and the most dense parts of the system. So we choose neutron stars that resemble in a way the neutron stars that we know that have merged in the very famous gravitational wave event from 2017, which had low masses. So here we're producing a hypermassive neutron stars of 2.9 solar masses because we're merging two of about 1.45. And I'm looking at a specific time of 5 milliseconds, a few milliseconds after the merger, because if you wait a few more milliseconds past 5, when you get around 8, 10, this will already collapse to a black hole because neutron stars of 3 solar masses are not stable. And we know that this was the case in this merger. So looking at the phase diagram, let me start with the diamonds. They show the densest part, which just as function of time, so getting from light green to dark green, you just get denser and hotter. So there's no surprise there. But the interesting part is this other region here shown by the beige circles. So when you're merging, and Matthias Hanowski and also Braunschweig yesterday explained in detail how this happens. When you have two stars that are merging, because you have the residue from this original position of the stars, you form this very hot ring. And so you have this region with a very large temperature outside the center. But what I found out is that as time passes, and eventually you cross the threshold for the confinement in the center of the star, suddenly the center of the star becomes hotter. Because, you know, when you pass through a first order phase transition, there's a small softening there and it just compresses and heats up. So the hottest part of the star, which was the ring, all of a sudden became the center. So the circles coincide with the diamonds. And I was just introducing the notation because what I really wanted to show you today is what's the charge fraction and charge chemical potential for the matter in these mergers, because we want to, again, be able to compare these together in phase diagrams together with other quantities. So the hottest part, you can think about the more outside part earlier on, and this is the central part shown by the diamonds in green. I'm just looking at the bottom part first of the left figure. And as happened in a normal neutron star, as you're getting more to the center, your charge chemical potential becomes more negative, meaning you're getting more farther from just having neutrons, having more protons and electrons. And at some point, you cross the threshold for the phase transition. And what happens in the quark phase is that you have, going to the top of the left figure now, you have a lot less, a much smaller charge chemical potential. And how this reflects in charge fraction is that because you're going from hadronic, or mainly hadronic, to quark matter, see some weird yellow lines appearing where I'm clicking my mouse. Okay, you never get to a large charge fraction that people were expecting to see in the first place. So when this first transition happens, the charge fraction lowers again, and you never cross a threshold of 0.15. And remember, we're comparing these with charge fractions of 0.4, 0.5. And, you know, if you're talking about cold neutron stars, you can think that you can discuss if there's a deconfinement to quark matter or not. But I think when we're talking about neutron star mergers, and there's also showing in the slide before, we're talking about going close to 60 MeV in temperature, besides densities of many, many times saturation density. I'm showing here chemical potentials about 1500 MeV. It's pretty impossible to think that you will not produce quarks in such regime of energies. So if you cannot get rid of the quarks, as a consequence, your charge fraction will never be large. So I get to my conclusions. And I want to point out that my talk was very complementary to the one that Jan gave before, because he was showing you in detail what happened to the heavy ion collisions. And I want you to keep in mind that if you go to lower energy heavy ion collisions, he was talking about a few entropies of maybe 3 or 4 entropies per baryon. If you go to low energy heavy ion collisions, the conditions are similar in temperature and entropy to the conditions in neutron star mergers, but you have to always keep in mind that there are differences, like, for example, the charge and isospin fractions and respective chemical potentials, and these do affect the position of the confinement. I put some number here. For the baryon chemical potential, you can have changes of 130 MeV, and for the charge chemical potential of about 330 MeV. So, you know, if you happen to find the confinement, for example, in the HIC beam energy scan phase 2, you know, it doesn't mean that that number translates exactly to what you expect from neutron star mergers. So there are many differences besides the leptons. I was talking a lot about charge, but also difference in strangeness. And but in my opinion, neutron star mergers create a very, very perfect conditions for the confinement. Again, because not only they're hot, but they have a smaller charge fraction, which helps a little bit. So we're recently learning a lot about neutron-star mergers because of all the gravitational waves that we have been seeing from different mergers. One is confirmed for neutron stars, maybe 2 or 3. And I think in the future we'll have a lot more. So maybe if we're lucky, we're going to be able to observe the post-merger part of the signal which we haven't observed yet. And if that's the case, we finally be able to learn more about the confinement of quark matter in these objects. Thank you.
Thank you for a nice talk. And there was the first question in the chat already. What are the relations on the 10th transparency, relations of densities?
So I never showed a phase diagram for baryon number density. I just indicated where they increase. But we have also published in the papers phase diagrams just like this one, but with density in the x-axis. Okay. If you're asking about a specific number, we can reach easily more than I would say 10 times saturation density when you're already about to collapse to a black hole.
Natalia, do you want to phrase your question?
Yes, I'm sorry. This is just a clarifying question. At transparency 10, you have mentioned some relations. I skipped this. What are the relations of densities or what?
So sorry, I didn't write here. So these are the charge fractions for the expected for the different environments.
So in fact, densities.
Those are charge fractions. So the number of charged baryons and
yes.
quarks over the total number.
Thank you. Thank you. So, thank you.
Okay, thank you. David?
Yes, I know you have already mentioned and discussed these differences between phase diagrams in heavy ion collisions and in astrophysics. One important aspect could be the neutrinos. So in particular, when we go to temperatures above 1 MeV, then we have neutrino trapping, in particular of the early stages. And this could have influence on the position of the phase border. Do you know if, I know this is a very complicated problem, in particular to include neutrino transport in the merger calculations. As far as I know, nobody has yet included neutrinos into the merger calculation. Is that right?
There's a simple neutrino leakage scheme in this merger simulations that the group of Luciano has developed. But I know there are groups in the US that are actually developing many techniques to deal with the neutrinos.
Yeah, so I mean, we have this Tobias Fischer, we have this supernova code, which has Boltzmann transport of neutrinos included, but nothing similar like this exists yet, as far as I know. But it is still worse because the massive presence of neutrinos influences on the beta equilibrium here, and as you have discussed, on the position of the phase border, right? And this could give a positive or a negative back reaction to the effects of a phase transition during the merger, right?
But not really pressure, right? The neutrinos wouldn't have a contribution or the electrons significant to the pressure to change the position of the phase transition.
It depends, of course. We know the phase diagram, which was also calculated in Frankfurt with Michael Bubala and his group, where they have included then color superconductivity, then it really changes the phase border.
Well, for the color superconductivity, you have to have a large quark gap to change it, right? Like 50? I don't. You were there.
No, okay. You have in the beta equilibrium, you have the chemical potential for the neutrinos. That makes a difference.
So the way I did it, included from my side. So they're just included as a free gas from their side, directly in the merger calculation. I just provide a hadronic part and quark part.
Oh, yeah. Okay.
Let's say further discussion for the.
Sure.
Yeah, and also Anirban, if you save your question, we can come back to it later. So we can thanks Veronica again.